A digital map on your screen is built from perfect mathematical vectors. But look closely at that same map printed on a page. Those pristine lines are an illusion, constructed entirely from microscopic, overlapping dots of physical ink. Building an accurate layout in GIS or design software is only the first phase of the cartographic process. To move spatial data from a digital environment of glowing RGB pixels onto a physical substrate like paper requires a complex mechanical translation. Failing to anticipate the limits of the printing hardware ruins projects. A flawless digital layout will yield blurry, misregistered colors and thick ink that physically flakes and cracks along the fold lines of the paper. To prevent this, we have to trace the exact pipeline this data travels through, starting in software processing, moving into optical physics, and ending on the heavy machinery of the printing press. Mastering this hardware translation is the only way to guarantee your spatial data survives in the real world. Every physical printing device shares a core mechanical limitation. They can only deposit ink onto a rigid grid of specific physical locations. They do not understand vectors or abstract geometry. Because of this limitation, every digital map passes through a raster image processor, or RIP. The RIP is the engine of the printing process. It takes page description languages, like PDF, and converts those instructions into a final raster grid of pixels the printer can execute. This mandatory conversion is why rasterizing a map too early in your workflow is dangerous. Low-resolution conversions create jagged, pixelated edges on fine vector lines and typography. Cartographers must maintain their original vector source files for as long as possible, relying on the RIP to handle that final physical grid conversion at the exact resolution of the output device. A printing press cannot print a lighter, diluted version of black or cyan ink to create a smooth gradient. It only holds solid, opaque inks. To simulate a vast spectrum of lightness and continuous terrain tones, printers rely on an optical illusion called screening. By printing a pattern of small ink dots and leaving small spaces of the underlying white paper visible, the human brain is tricked into blending them together, perceiving a lighter, continuous tone. The most common professional method is halftone screening. This diagram shows how halftones alter the physical size of dots on a rigid grid. Smaller dots allow more white paper to show through, resulting in lighter tints. Larger dots cover more paper, creating darker tints. Inkjet printers use a different technique, stochastic screening. Look at panel B. Instead of altering dot size, stochastic screening uses uniformly tiny dots, but alters their spacing. Because the placement is pseudo-random and scattered, it prevents unwanted visual interference, known as moire patterns. Understanding these screening geometries allows you to predict exactly how a digital elevation model or complex gradient will physically render when it hits the paper. To create a full-color map, presses use the subtractive color model. 4 translucent inks, cyan, magenta, yellow, and black, are applied in overlapping layers. If you use halftone screening for all 4 colors on the exact same grid, the dots will print directly on top of one another. To fix this, the individual grids must be rotated to mathematically offset angles. When these angled grids overlap correctly, they form tiny circular clusters called rosettes. The eye interprets these overlapping dots as solid, vibrant secondary colors. However, the CMYK gamut has strict physical limits. Certain vibrant oranges, greens, or highly specific administrative boundary colors are impossible to reproduce accurately simply by mixing those 4 base inks. When exact precision is required, cartographers use spot colors, like the Pantone system. These are completely opaque pre-mixed inks that bypass the CMYK gamut limitations entirely, though requiring a dedicated printing plate drastically increases production costs. Printed color is never an absolute truth. It is an engineered optical illusion. Cartographers verify their on-screen choices by reviewing highly accurate physical contract proofs before the final print run begins. When a map requires more than 200 copies, low-volume digital methods become too expensive. The industry standard for mass reproduction is offset lithography. This process relies on chemical separation. A laser engraves a metal printing plate so that the image areas attract oil-based ink. The non-image areas are coated with a thin film of water, which naturally repels the ink. The term offset describes the indirect path the ink takes. The top plate cylinder transfers the ink onto a middle rubber blanket cylinder, which reverses the image, before finally pressing the ink onto a sheet of paper passing underneath over the impression cylinder. This intermediate rubber blanket is necessary. It protects the fragile, expensive metal plate from abrasive wear, and its soft surface pushes the ink efficiently into the porous fibers of the paper. A full color map requires the paper to travel through 4 of these units in sequence at high speed. This creates the challenge of registration, the strict mechanical requirement that the cyan, magenta, yellow, and black layers perfectly align. Because heavy machinery inevitably shifts by tiny fractions of a millimeter, slight misregistrations create thin white gaps between colored polygons. Prepress operators fix this using trapping, a digital technique that slightly overlaps adjacent colors in the software to hide those mechanical shifts. The physical inaccuracies of heavy machinery literally force cartographers to alter the true geometric boundaries of their digital data to maintain the illusion of visual perfection on the page. The physical reproduction method is not an afterthought added at the end of a project. It is a rigid constraint that dictates your entire design process from the start. Before drawing a single line, you must define the logistics, the total budget, the opacity of the media to prevent ink bleeding through, the exact paper thickness to prevent cracking, and how the printed legend will align with the mechanical folds. You must also relentlessly edit the digital file, but self-editing is hindered by psychological hurdles. Overfamiliarity causes your brain to fill in the gaps of what you meant to draw, and fatigue makes obvious spelling errors invisible to the eye. To combat this, cartographers employ visual disruption. By isolating small sections of a large layout, or even rotating the entire digital map upside down on the monitor, you force your brain to analyze shapes and patterns rather than reading the map as a familiar conceptual image. A successful map requires merging digital precision with an intimate knowledge of mechanical output. Your spatial data must not only be geometrically accurate on a glowing screen, but robust enough to survive the physics, chemistry, and heavy machinery of physical reproduction.